This is a lecture about percent composition and empirical formula. Both of these phrases give us information about compounds as far as the elements that are present in them. Percent composition lists the amount of a certain ingredient that we're interested in comparison to the amount of the whole package, or the amount of everything that's in something. And of course, since it's percent, it's always times 100. Percent composition is what the expression that ingredients for most edibles and most personal care products are used. So food item might give you the percent fat, or it might give you the percent sodium present. And so it's important to understand what percent composition means and how we calculate it. Oh, this was just an example I wanted to show you on any nutrition label. The percents that are given are percent by mass, which is what we'll be learning about today. All right, the formula for calculating percent composition is at the bottom here, so you want to make sure you understand and know how to use this formula. The percent of any element, okay, is the number of atoms of that element. So if there are 2 sodium in a compound, then there would be the number 2 here, for example. The molar mass of that same element, okay, so you're trying to figure out how many of each element there are and times the mass of the element, divided by the molar mass of the entire compound. Percent is always part over whole times 100, okay? And in this case, the part is the mass of a certain element and the whole is the mass of the entire compound. So for example, I might ask you, typical problem, what's the percent composition of this compound? If you're just generically asked what's the percent composition, they want to know the percent of each element in that compound. So in this case, what's the percent carbon and what is the percent hydrogen? This is propane, by the way. That's the gas that fuels your barbecue grills. So again, I wrote down the formula for percent composition. Again, commit that to memory. That's pretty easy. All right, so let's do percent carbon. First thing you do is count how many carbon atoms are in the compound you're talking about. In this case, there are 3. The molar mass of carbon is 12.01. You get that off the periodic table. The molar mass of the entire compound, C3H8, is 44.1. You do that just by adding up the masses of every single element in the compound. Turns out when we do that, multiply by 100, we see that carbon is 81.7% by mass of propane. We can go through the same type of calculation for hydrogen. There are 8 hydrogens in propane. Each hydrogen has a mass of 1.01 gram. Multiply by 100, of course, and we see that hydrogen is 18.3%. A little shortcut, if you only have 2 elements, you know that the percent of all the elements in a compound have to add up to be 100. So if you only have 2 elements and you figure one of them out, you can figure the other one out simply by subtracting the first one from 100. So 100 minus 81.7 is in fact 18.3. All right, so you go ahead and try it yourself now. Try to calculate the percentage of carbon, hydrogen, and oxygen in this compound. That happens to be sucrose, sugar, table sugar. So when you're done, you should have a value for percent carbon in sucrose, the percent hydrogen in sucrose, and percent oxygen in sucrose. I would stop the video now, pause it, and go ahead and work those out, and then start it again and see if your answers are right. So here we go. If you have time, it's always smart to do a double check, and the way to do that when you're doing percent calculations is to add up all the percents. They should add up to be 100. If they get it to be like 99.7 or 100.2, that's perfectly fine. That's just rounding and stuff. Alrighty, so now we are going to talk about different types of chemical formulas. There are empirical formulas and molecular formula. The empirical formula, the easiest way to think about it, is a mathematically simplified formula. The molecular formula is the real chemical formula of the compound, not simplified, nothing has been done to it. So for example, if you look at the molecular formula for glucose, C6H12O6, you can see that it can mathematically be simplified. If you divide each subscript by 6, you get the empirical formula of CH2O. So CH2O is the empirical formula of glucose, and the molecular formula is C6H12O6. Sometimes the molecular formula and the empirical formula are the same. For example, water, H2O, cannot be simplified, which means the molecular formula and the empirical formula are the same for water. All right, so you can get empirical formula from percent composition data. It's about a 4 or 5 step process, and so make sure you work a few of the problems just to imprint the calculation. They are not hard calculations, but you need to do enough of them so that you can remember how to do them. Why do we care about empirical formula? I know I used to ask that, because when a chemist gets an unknown compound and they start analyzing samples of it and different equipment they have, typically what they'll get is ratio of elements that are present in the compound. So rather than getting an actual formula, let's say C10H22O8, I'm just making something up. Instead of getting the exact formula, they may get a ratio, in other words, an empirical formula that would be like C5H11O4, and so then they have to do further work to decide whether or not the empirical formula they got was the actual formula or some simplified version. And so it's important for chemists to be able to work with empirical formulas. So here's an example. I always like to teach with examples if possible. The 4 steps for finding empirical formula from percent composition are listed here. They will make more sense as I do the sample problem. The first thing you want to do is change the percent to mass. Notice that you're starting with percent composition data, so all of the data is in percent. You want to change that to mass. I'll discuss that in the next slide. Then you want to convert mass to mole. You want to divide all of the values you get by the smallest mole value so that you can get some ratios. And the multiply thing, sometimes you need to do that. I'll discuss them all. So here we go. All right, first of all, change your percent signs to mass. If we assume we have 100 grams of a sample, it is in fact true that percent equals grams. So we had 61.31% carbon. If we had a 100 gram sample, we're just going to make that assumption, 61.31% really would be 61.31 grams. So bottom line, change all your percent signs to grams, and you're good to go on step 1. 2, calculate the moles of each of the elements from the grams you have. So 61.31 grams of carbon, divide by its molar mass that you get from the periodic table, and that will give you moles of carbon. Do that for each of the elements. So you have mole values for all the elements. Is to find the smallest mole value that you just calculated and divide each of the mole values by the smallest value. So the mole values you got, 5.105 moles of carbon, 5.09 moles of hydrogen, etc. The smallest of those 4 values is 0.7288. So you take that smallest mole value and you divide each of the mole values by that. You're hoping to get whole numbers now so that you can write out your empirical formula. if you get a number after dividing by the smallest mole value that's within, let's say, 0.1 of a whole number, you're fine, you can round. Okay? So in this case, we're very close to whole numbers. We're definitely within 10%. And so our empirical formula is 7 carbons. You use a subscript to show that. 7 hydrogens, another subscript. 1 nitrogen, that 1 is understood, you don't have to write it in. And 2 oxygen. So the empirical formula for this compound is C7H7NO2. Now, there are some cases when you divide by the smallest mole value and you do not get within 0.1 of a whole number. That'll be in this example, and I'll show you what to do. In that case, you have like a 5th step. So I would recommend at this point you turn off the PowerPoint and you go ahead and work through the steps. I cannot emphasize enough that the success to chemistry is working enough problems so that you don't even have to think about formula or what you do, that it almost becomes routine. When you're done working this out, come back and you can compare your answers. All right, so again, the first step is to change the percent signs to grams. Second step is to convert all of your gram values to mole values by dividing with the molar mass of each of the elements. The third step is to divide each of the mole values you just calculated by the smallest mole value. What is the smallest mole value here? 3.406. So each of them are divided by 3.406. And here are our values, 1, 1.3, and 1. Remember the rule of thumb I told you that after you divide by the smallest mole, if all of your mole values are within 0.1 of a whole number, you can round. 1.33 is not within 0.1 of a whole number. So in this case, we've got to do the 5th step, which is multiply our mole values by some integer that will make each mole value be a whole number. So if you're not sure just by, like I can look at 1.33 and I just know in my head that if I multiply all of these subscripts by 3, I'll get whole numbers. If you don't see that intuitively, just start multiplying the subscripts by whole numbers, by 2, by 3, by 4. The whole number you'll multiply by will be one of these, 2, 3, or 4. I've never seen it be higher than 4. So let's go ahead and multiply all these by 3. What do we get? We get C3, because 1 times 3 is 3. We get H4 and O3. So our empirical formula now is C3H4O3. All right. And that, my friends, is the end of learning about percent composition and empirical formula.